What if I told you that right now, scientists are debating which cosmic monster holds the title of the universe's most massive black hole? In one corner, TON 618, weighing 66 billion suns, shining brighter than 140 trillion stars. In the other, Phoenix A, potentially 100 billion solar masses, defying every theoretical limit we've ever calculated. But here's the twist: we might have discovered both of them are breaking the laws of physics in completely different ways. Let me blow your mind with what we're dealing with here. Phoenix A's event horizon has a diameter of 590 billion kilometers, that's 100 times the distance from the Sun to Pluto. If you traveled around it at light speed, it would take you 71 days and 14 hours. TON 618's event horizon, 1,300 astronomical units across, so massive that our entire solar system would fit inside it 40 times over. But in January 2026, literally this month, astronomers discovered a black hole growing at 13 times the Eddington limit. That's the theoretical maximum speed any black hole should be able to grow. And in December 2025, scientists published a groundbreaking study proving that the relationship between X-rays and ultraviolet light in quasars has fundamentally changed over cosmic time. This means the rules governing TON 618 and Phoenix A weren't the same when they formed. The early universe was a completely different battleground. So which one is actually the king? The answer is more complicated, and more mind-blowing, than you think. Before we crown a champion, you need to understand what makes these objects so impossibly massive. In our standard model of the universe, supermassive black holes grow through a slow, predictable process. They start as stellar black holes, maybe 10 to 100 times the Sun's mass, formed when massive stars die. Over billions of years, these black holes merge with each other. They consume gas, dust, and occasionally entire stars. This gradual growth is governed by something called the Eddington limit, a theoretical boundary where radiation pressure from all that infalling matter should balance the black hole's gravity, preventing it from eating any faster. Our own Milky Way has a supermassive black hole called Sagittarius A star. It weighs about 4 million solar masses and took 13.8 billion years to reach that size. That makes perfect sense. The timeline works. The physics checks out. Now here's where things start to break down. Phoenix A weighs 100 billion solar masses, that's 24,100 times heavier than Sagittarius A star. TON 618 weighs 66 billion solar masses, still 16,500 times heavier than our galaxy's black hole. And both of these monsters existed in the early universe. Phoenix A is located 5.8 billion light-years away. TON 618 is 10.4 billion light-years distant. That means we're seeing TON 618 as it existed when the universe was only 3 billion years old. Phoenix A existed when the universe was about 8 billion years old. Think about what this means. TON 618 had less than 22% of the current age of the universe to accumulate 66 billion solar masses. That's like watching a newborn elephant grow to the size of Mount Everest in just a few months. The math doesn't just bend, it shatters. This is where things get strange. What I'm about to reveal will completely change which black hole you think deserves the crown. But before we dive into the epic discovery stories behind both titans, hit that subscribe button. We're tracking every major breakthrough in 2025 and 2026, and the discoveries coming out right now are absolutely rewriting what we thought we knew about the universe. You're not going to want to miss what happens next. Let's start with TON 618's origin story. In 1957, two astronomers at Mexico's Tonantzintla Observatory, Braulio Iriarte and Enrique Chavira, were photographing what they thought were faint blue stars. Entry number 618 appeared, decidedly violet, on their photographic plates. They had no idea they'd discovered one of the universe's most extreme objects. Quasars wouldn't even be recognized as a class until 1963. Fast forward to the early 2000s. A team led by astronomers Schemmer and colleagues analyzed TON 618 spectral lines in unprecedented detail. They measured emission line widths showing gas moving at 10,500 kilometers per second. Only one force could accelerate matter that fast, a black hole weighing 66 billion solar masses, making it the most massive black hole known at the time. Now, Phoenix A's story is equally fascinating but more recent. In 2010, the South Pole Telescope detected something extraordinary during a survey of the southern sky. They found the Phoenix Cluster, one of the most massive galaxy clusters ever discovered, emitting more X-rays than any other known cluster. When astronomers turned their instruments toward the cluster's central galaxy, Phoenix A, they found something that shouldn't exist. Using a technique called adiabatic modeling, tracking how the central black hole fuels its own growth through the behavior of hot gas, a team led by M. Brockamp calculated that Phoenix A's central black hole could weigh up to 100 billion solar masses. But here's the kicker, this measurement wasn't made through direct orbital mechanics like most black hole mass estimates. It was inferred from the extreme behavior of the surrounding gas and the black hole's incredible influence on the entire cluster. Some estimates put it at 100 billion solar masses. Others suggest it might be even more massive. In 2019, NASA's Chandra X-ray Observatory revealed something mind-blowing about Phoenix A. The black hole was actually undersized compared to its galaxy, allowing gas to cool and trigger the highest star formation rate ever recorded in a galaxy cluster center, 500 solar masses per year. That's 500 times faster than the Milky Way produces stars. This weakened black hole had let its galaxy awaken with a massive starburst. But as it grew, it was catching up, fast. So how do these two titans actually stack up? TON 618 is a hyperluminous quasar, one of the brightest objects in the entire universe. At its peak, it shines with the brightness of 140 trillion suns. That's because it's actively consuming matter at a ferocious rate. Gas spirals into its accretion disk at relativistic speeds, heating to millions of degrees and releasing more energy than anything else we've ever observed. In 2021, the Atacama Large Millimeter Array discovered a Lyman alpha blob around TON 618 that's 330,000 light-years across, twice the diameter of the Milky Way. This glowing nebula contains 50 billion solar masses of gas PR component. The environment around TON 618 is so extreme that it's regulating galaxy formation across distances we can barely comprehend. Phoenix A, on the other hand, operates differently. It sits at the center of the Phoenix cluster, surrounded by one of the most extreme environments in the universe. The cluster contains enough hot gas to outweigh all the galaxies combined. This gas is cooling at a rate of 3,280 solar masses per year, the highest cooling flow rate ever recorded. Phoenix A's event horizon, if it's truly 100 billion solar masses, would have a Schwarzschild radius of 295 billion kilometers. That's about 2,000 astronomical units, or 50 times the distance from the Sun to Pluto. The circumference of its event horizon would take light 71 days to traverse. According to research from December 2024, Phoenix A may represent the upper limit of how massive black holes can actually grow. Scientists led by Priyamvada Natarajan at Yale University calculated that supermassive black holes create their own growth cap. As they consume matter, the radiation pressure they generate starts pushing gas away, preventing even faster growth. If Phoenix A truly is 100 billion solar masses, we may be looking at the physical maximum size a black hole can reach through normal accretion processes. It's the ultimate heavyweight champion, not because it beat TON 618, but because it literally can't get any bigger. But here's where the plot thickens. Just when you thought you understood which one is bigger, the scientific community dropped a bomb. Phoenix A's mass has never been directly measured using orbital mechanics. The 100 billion solar mass estimate comes from modeling, from watching how it affects surrounding gas and the cluster dynamics. Some recent estimates actually put Phoenix A closer to 20 to 30 billion solar masses, which would make TON 618 the clear winner. Meanwhile, TON 618's mass is measured through spectroscopic analysis, watching how fast gas moves in its vicinity. Early estimates said 66 billion solar masses. Some calculations pushed it as high as 40 to 66 billion solar masses with significant uncertainty. Then in January 2026, literally 2 weeks ago, astronomers discovered a quasar called Epheds J084222.9 plus 001000 growing at 13 times the Eddington limit. 13 times. This black hole is breaking every rule we thought governed black hole growth. Lead researcher Sakiko Obuchi from Waseda University explained this could represent a transitional super-Eddington phase, where black holes rapidly surge in mass. What if TON 618 went through phases like this? What if it grew in explosive bursts rather than steady feeding? That would explain how it got so massive so fast in the early universe. And Phoenix A? In November 2025, scientists confirmed the first, runaway, supermassive black hole, a massive black hole ejected from its galaxy, racing through space at 2.2 million miles per hour, leaving a trail of new stars in its wake. What if Phoenix A is actually the merger of multiple supermassive black holes that collided shortly after the Big Bang? Then there's the discovery from December 2025. The relationship between X-rays and ultraviolet light in quasars has fundamentally changed over cosmic time. The rules that governed TON 618 in the early universe were different from the rules governing Phoenix A billions of years later. We might not be comparing apples to apples here. We might be comparing two entirely different classes of cosmic titans. So here's what I genuinely want to know from you: who do you think is the real king? Drop your vote in the comments. Option A, TON 618, 66 billion solar masses of pure, confirmed, quasar-powered dominance. Option B, Phoenix A, potentially 100 billion solar masses, pushing the theoretical maximum. Option C, it's a tie, they're both kings ruling different eras of the universe. Or do you think we haven't found the true king yet? Because with discoveries like the one from January 2026 showing black holes breaking the Eddington limit by 13x, who knows what monsters are lurking out there waiting to be discovered? I genuinely want to hear your thoughts on this cosmic battle. The implications of this battle extend far beyond just crowning a champion. These two objects are teaching us fundamental truths about how the universe evolved. First, galaxy formation. Both TON 618 and Phoenix A show us that supermassive black holes don't just sit passively at galaxy centers, they actively shape the formation of stars, the distribution of matter, and the evolution of entire galaxy clusters across hundreds of thousands of light-years. Second, the limits of physics. If Phoenix A truly represents the maximum mass limit for black holes, then we've discovered a fundamental boundary in nature. Black holes can't grow forever, they create their own ceiling through radiation pressure. That's a profound insight into how the universe self-regulates. Third, the mystery of rapid growth. The discovery in January 2026 of super-Eddington accretion happening at 13 times the theoretical limit changes everything. If black holes can temporarily break these rules during transitional phases, then both TON 618 and Phoenix A could have grown through explosive bursts we're only now beginning to understand. And finally, primordial black holes. In January 2026, astronomers using the James Webb Space Telescope discovered a 50-million solar mass black hole in galaxy Abell 2744 QS01 that may be one of the first black holes formed directly after the Big Bang. If Phoenix A is a primordial black hole, born directly from the collapse of massive gas clouds, then it represents a completely different formation pathway than TON 618. This battle isn't just about which one is bigger. It's about understanding how the universe built its most extreme structures. But here's the hopeful part, we're closing in on answers. The James Webb Space Telescope is revolutionizing our understanding of early universe black holes with discoveries almost every week. The Nancy Grace Roman Space Telescope, launching in 2027, will survey the sky 200 times faster than Hubble, potentially finding thousands more ultramassive black holes. The European Extremely Large Telescope, coming online later this decade with its 39-meter mirror, could potentially resolve the gas dynamics around both TON 618 and Phoenix A with unprecedented clarity. In December 2024, scientists published new methods for accurately measuring ultramassive black hole masses using galaxy core sizes, a technique that could finally give us direct measurements of Phoenix A's true mass. The championship bout isn't over. We're just getting better referees. Science is making progress every single day, and the mysteries of TON 618 and Phoenix A are slowly yielding their secrets. But this isn't the only cosmic battle happening right now. There's the densest cluster of supermassive black holes ever found, 11 quasars packed into just 40 million light-years, with odds of 1 in 10 to the power of 64 of happening randomly. There's the runaway black hole confirmed in December 2025, racing through space and leaving a trail of stars in its wake. And there's the ultimate question, if TON 618 grew to 66 billion solar masses when the universe was only 3 billion years old, what has it become now, 10.8 billion years later? The light we see is ancient history. What is TON 618 doing right this second? If you want to follow this cosmic championship season, subscribe and hit that notification bell. Thank you for joining me in this ultimate showdown between the universe's heavyweight champions. Whether you're Team TON 618 or Team Phoenix A, one thing is certain, we're privileged to live in an age where we can witness these cosmic titans and unravel their secrets. The battle for the crown continues. And honestly, the universe keeps surprising us with even bigger mysteries. Keep looking up. The cosmos has more champions waiting to be discovered. See you in the next one.